A healthy mouse, suddenly unable to use its front paw. But this wasn't the result of a tragic accident, nor was it the work of a disease. Scientists did this deliberately. But that wasn't the most disturbing part of the experiment. What came next sounded almost cruel. They took away the mouse's remaining healthy paw, too. They forced the animal into a reality no living creature would ever choose for itself. To an outside observer, it looked like pure torture. The mouse stumbled across its enclosure, reaching for food and missing, falling every time it tried to climb. But behind this apparent cruelty was a desperate quest to answer one profound question. Within weeks, the impossible happened. The limb that was supposed to be permanently dead slowly began coming back to life. The mouse was climbing, grasping, and rewiring its own biology, simply because the easier path had been stripped away. This single, extreme experiment birthed a medical revolution known as constraint-induced movement therapy. But what sparked this radical idea in the first place? The scientist most closely associated with the idea was psychologist Edward Taub. For years, Taub had been studying how animals responded to injury. Again and again, he noticed something strange. The body often appeared capable of more recovery than anyone expected. The real mystery was why that recovery so often failed to happen. Most researchers assumed the answer was simple. The injury itself was the problem. Damage the nervous system and function disappears. But Taub suspected something else was happening. He believed behavior might be trapping the animal in its own disability. To test the idea, researchers created experiments involving impaired limbs. The setup was straightforward. One limb was weakened or deprived of normal function. Then the animals were observed over time. At first, everything unfolded exactly as expected. The animals stopped using the affected limb. Instead, they relied entirely on the healthy one. Every task was performed with the stronger side. Every success reinforced the same lesson. Use what works. Ignore what doesn't. The adaptation seemed logical, but it created a hidden problem. The less the impaired limb was used, the weaker it became, the less likely the animal was to try using it again. A vicious cycle emerged. Failure led to avoidance. Avoidance led to more failure. Researchers eventually gave this pattern a name: learned non-use. The limb was not completely incapable of movement. The animal had simply learned that using it was frustrating and ineffective. Every failed attempt became evidence. Don't use that paw. Use the other one. Day after day, the lesson became stronger, and eventually the damaged limb was almost completely abandoned. This was the moment the experiment took a dramatic turn. The healthy limb was restrained. The easy solution disappeared. The animal could no longer depend on its strongest paw. Everything now depended on the limb it had spent weeks avoiding. At first, the results looked brutal. The mouse struggled constantly. Simple tasks became difficult. Progress seemed painfully slow. To an outside observer, it might have looked cruel. But beneath the surface, something extraordinary was happening. The brain was being forced to solve a problem it had stopped trying to solve. Neural circuits that had fallen silent began activating again. Connections started strengthening. New pathways began forming around damaged areas. The nervous system was adapting. The brain was rewriting itself. Day after day, the mouse improved. Not because the injury vanished, not because the damaged tissue magically healed, but because the brain discovered another route. Scientists began measuring the changes. The evidence kept pointing in the same direction. The nervous system was far more flexible than anyone had imagined. Functions that appeared lost could return. Skills that seemed gone forever could re-emerge. The brain was not a machine with fixed wiring. It was something much more dynamic, something capable of change. The implications were enormous because the experiment was never really about mice. It was about people. Every year, millions of stroke patients face a similar problem. A stroke damages part of the brain. One arm becomes weak. One hand becomes difficult to control. Naturally, the healthy side takes over. The patient learns to rely on what still works. Life becomes easier that way. But the same cycle begins. The affected arm is used less. The brain receives fewer signals from it. Recovery slows, and eventually the person may stop trying altogether. The experiment suggested a shocking possibility. What if part of the disability wasn't caused by the injury alone? What if some of it was caused by learned non-use? What if the brain still had untapped potential waiting to be activated? Researchers began testing the idea in human patients. The results surprised even many experts. Patients who had struggled for years began recovering movement. Some regained the ability to grasp objects. Others learned to perform tasks they thought were permanently impossible. The therapy spread around the world. Hospitals adopted it. Rehabilitation centers embraced it. And countless patients benefited from a lesson first revealed by laboratory animals. But perhaps the most fascinating part of the story has nothing to do with medicine. It has to do with human nature. The mice recovered only after their preferred solution disappeared. As long as the healthy paw remained available, the damaged one had no reason to improve. The easy path prevented adaptation. The struggle created it. Systems grow stronger when they are challenged. Abilities develop when they are tested. Recovery is also shaped by behavior, by repetition, by persistence. Sometimes the limits we accept are not the limits we actually have. And sometimes the path to recovery begins the moment the easier path is taken away.